For more videos like this for discrete 1, you can check out Sarai's studies. Link is in the description box below. Welcome to the first video on set theory. Now, what is a set? A set is a collection of unordered and unique elements, like numbers, letters, objects, or even other sets, that are contained by curly braces. Sets are also denoted using capital letters. For example, we can have a set A that contains the elements 1, 2, 3, and 4. We can have a set B that contains the elements 1, 3, 2, and 4. Now, this goes to show that when the definition says that a set is a collection of unordered elements, it doesn't mean that the elements of a set have to be out of order. It just means that the order does not matter. So here the elements are in order, it's still a set. Here the elements are out of order, it's still a set. So because the order does not matter, these are the same sets, as they contain the same elements. Now, another condition that the elements of a set have to satisfy is that the elements have to be unique. Meaning, in a set, I cannot see 1 multiple times, nor can I see 2 multiple times, and so on. I can only see each and every single one of these elements exactly once in a set, which is true for this set, and it's also true for this set. I see 1 time, 2 1 time, 3 1 time, and 4 exactly 1 time. So the elements of both of these sets are unique. Another condition is that the elements of a set have to be contained by curly braces, and you see that all of the elements in both of these sets are indeed contained by curly braces, so that's good. And finally, sets are denoted. Denoted is another word for named, using capital letters. So notice that I named this set using capital letter A, I named this set using capital letter B. I can't say, oh, lowercase a is going to be equal to this set. No, we cannot use lowercase letters, only capital letters, to name sets. This goes to show if you have a set A that contains the alphabet as its elements, you can't use the capital version of the alphabet because these letters are reserved to name sets, not to be elements of a set. So you would have to have set A contain the lowercase version of the alphabet, which is obviously A, B, and C lowercase. Another example of a set would be set C that contains the elements 1, 2, 3, 4, and 4 again. Now notice that this set does not have unique elements. I see 4 2 times, and remember we can only see every element of the set exactly once. So often they'll give you sets like these to work with, but you have to know you can't work with these. You have to simplify them first by simply just removing any dupe that you see and just leaving all of the unique elements. So that set just simplified to this, which is conveniently the set containing 1, 2, 3, and 4, which is very similar to the set containing 1, 2, 3, and 4, and very similar to the set containing 1, 2, 3, and 4. In other words, these are the same sets. So let's say I had another set D that contains the elements 1, 2, and a whole other set. Remember that a set is a collection of elements that can contain numbers, just like 1 and 2, but can also contain other sets, just like this one right here. Now, something I do want to mention is, let's say I have a set E that contains the elements 1, a, house, plum, and pen. Is this a set? Well, Garcia didn't have this as part of his definition for discrete 1, but Hamidi, regardless of discrete 1 or discrete 2, her definition is this, plus the fact that all elements in a set should have something in common with each other. In other words, if you look at this set, in quotes, 1, which is a number, a, which is part of the alphabet, a house, which is an object, and plum and pen, which are words, have nothing in common with each other. They're not part of the same world. So for Hamidi, this would not be a set. And you can double check with Garcia about his opinion on this, but for Hamidi, if you say that this is a set, you will get points off. Now, as for some notation, recall that all of these values in a set are called elements, but we can also call them members. So 1 is a member of set A, it's also an element of set A. 2 is a member of set A, is also an element of set A. But how can I mathematically write that 1 is an element of set A? Well, we would use this symbol, which means is an element of, or is a member of. So we would say 1 is an element of set A, or 1 is a member of set A, or 1 is part of A, or 1 lives in A. So if you think of A as a house, and these are all of the people living in it, these are the members of the house. These are the elements of the house. So 1 lives in house A, 1 is part of house A, 1 is an element of set A. However you want to think about it. But I can say the same for 2 is an element of A, 3 is also an element of A, and I can say the same for 4 is an element of A. For set B, I could say that 4 is an element of set B, because 4 is indeed an element of B. For set C, I could say that 3 is an element of set C. For D, I could say that this entire set is an element of set D. I can also say that 1 is an element of set D. I could also say that 2 is an element of set D. How would I mathematically write if an element is not in a set? Well, I know that 5 isn't in this set, so I can say 5 is not an element of set A. So you just take the sign and put a line through it, just like if you have an equal sign and you put a line through it to say not equal. Now I want to introduce to you cardinality. Cardinality is just a fancy way of saying the size of a set. In other words, how many elements are in a set. You're just counting. So we denote the cardinality of set A by simply adding absolute value signs around it, or you'll see the cardinality, since it's just counting the number of elements in a set, is going to be the number of elements in set A, so n for number of elements. So if we count the number of elements in set A, well, that's 1, 2, 3, 4, so the cardinality of set A is 4. If we want to find the cardinality of set B, just count 1, 2, 3, 4 elements, so the cardinality is 4. The cardinality of set C is 1, 2, 3, 4, cardinality is 4. If we want to find the cardinality for set D, that's 1, 2, 3 elements, so the cardinality is 3. The last thing I want to do is introduce to you two special sets. The first one is called the empty set, also referred to as a null set, and it's literally an empty set. That's it. You will also see it denoted more often with the phi symbol. So this is the phi symbol. It's just a circle with a line through it. And the second set we call the universal set, which is denoted as a U with these lines slanted up above, or simply just a U. So the idea of the universal set is that it doesn't contain everything in the universe. It just contains everything in the universe that we care about in the context of our problem. So if we're working with sets that only contain numbers, then the universal set would contain all numbers. If we're working with sets that only contain colors, then the universal set would be all colors. From a statistic perspective, if you take in statistic, the universal set is basically the population, and then any set within the universal set is what you call a samples. So here this could be set A, it has maybe red and blue, and this is set B that has yellow and green. We're working with these sets, and the universal set would be all colors: purple, indigo, brown, red, blue, yellow, and green, because they're still inside this box in this universe. So that's the idea. And I'll have a good example for universal sets once we get to operations of sets. Now we have some practice questions, so let's go ahead and start. For the first one, is K an element of this set? Well, do I see K by itself in this set? Yes, I do. So it is true that K is an element of this set. For the second one, is a set containing K an element of this set? Well, do I see this entire thing inside the set? Yes, I do. It's right here. So it is true that the set containing K is inside this set. Is K an element of this set? Well, do I see just this as an element of the set? No. I see A as an element of the set. I see B as an element of the set. I see the set containing K as an element of the set, but I don't see K by itself. So it is false that this is an element of this set. In fact, K is an element of this set because it's inside this set. It's not inside this set. For the next one, remember that this is just the empty set. So it's really asking, is the empty set an element of another empty set? Well, do I see this inside here? No, I do not. If this was the question, then it would be true because I see this literally inside the set. So yeah, it's true that this is inside the set, but I don't see this inside this set. Now, is the empty set an element of this set? Well, this set just contains 0. I literally do not see this symbol inside the set, so it's false. Another way to think about it is this literally means the empty set. I don't see this symbol inside this set. If it was a set containing 0, comma the empty set, or the set containing 0, comma 5, which is the same thing as the empty set, then yeah, it would be true. I see this inside the set, but that's not the case. I just see 0, so it's false. This is not an element of the set. Now, do I see this inside the set? No, I just see the empty set. I don't see the set containing the empty set. If it was this, comma this, so the set containing 5, then yeah, you see this in here, so it would be true, but that's not the case. So it's false that this is an element of the set. Is the set containing 1 and 2 an element of this set? Another way to think about it is just say, do I see this entire thing in this set? Well, 0 is an element, the empty set is an element, and also the set containing 2 and 1. But remember that the order of sets does not matter. So this can be rewritten as 1, comma 2, which is indeed the same as this. So yes, you do see this inside this set. So it is true that this is an element of this set. Is the set containing the empty set an element of this set? Well, do you see this entire thing in here? No, I see it in here, but it's not an element of the set. It's an element of this set. So this is not an element of this entire set. So false. Is the empty set an element of this set? Well, do I see this inside the set? Yes, I do. For J, notice that we have a set and we have absolute values around that set. What does that mean? Well, recall that when we have absolute values around a set, that means it's asking for the cardinality, the size, how many elements are in that set. So you just count 1, 2, 3 elements. So the cardinality is 3. Now in this case, we have another set that contains the elements 0, the empty set, and the set containing 2 and 1. But it's inside n and parentheses. So remember that when we have n and a set, it's just asking what's the number of elements in that set. So what's the number of elements of this set? Let's count. We have 1, 2, 3 elements. So the cardinality is 3. And again, we don't count these as elements because these are not elements of this set. These here are elements of this set. We just want the number of elements of this entire set. And finally, if 60% of the United States population are male and 40% are female, then what is the universal set? In other words, what are you dealing with? You're dealing with a set of males. You're dealing with a set of females. So these are the two things that you're considering. So what is the universe of the things you're considering? Well, the universe is the entire population, the entire United States population. So you would write this as your answer. That's the universal set. And that's it for this video. In the next, we'll cover 3 different ways we can represent sets.